with chapter 26.5 about acylation. So maybe you ever heard the word about alkylation. What is alkylation? Alkylation is a process by which the alkyl group is introduced to another molecule. However, in this particular acylation process is that you attach this acyl group, you introduce it into your molecule. An acyl group is just look like this. You have the carbonyl group with the R group attached to it. Talk a little bit about carboxylic acids. So carboxylic acids are somewhat unreactive. Previously, we already saw that carboxylic acids can undergo several reactions. For example, when it comes to in contact with some base or the metal carbonates or metal. But actually, like carboxylic acids, later we will see it cannot undergo, like for example, the addition-elimination reactions, like what the acid chloride does. So, acid chlorides, it is actually the derivatives of carboxylic acids. It is when we change this OH in the carboxylic acids with the halide. Okay, and this acyl chloride has a good leaving group, which makes it more reactive compared with the carboxylic acids. Here are several other derivatives. For example, if you convert or if you change the OH with the OR, you will get the ester. And if you change the OH with the Cl, you get the acid chloride. And with the OCOR, you got the anhydride. And so this compound is called the ethanoyl chloride. Ethan because it consists of two carbons, and then the suffix will be with oil, il, and then the name of the halide ion attached to it. For the acyl chloride, it is easy to be attacked by a nucleophile or prone to be attacked by nucleophile. The nucleophile will attack the partially positive carbon center and then expel the leaving group here. Thus, the nucleophile will substitute the Z and then the halide ion will be expelled. And how readily or how well the reaction will go, it depends on three factors. The first one is the magnitude of the partially positive charge on the carbon center here. Yeah, so the more positive it is, then it means it is more easier to be attacked by the negative nucleophile. And what makes this carbonyl become, what will affect the magnitude of the partially positive charge on the carbon atom? It is depends on the Z, whether the Z is a electron releasing or donate the electron, or reversely it will attract the electron, right? So if the Z is good at attracting the electron or a good withdrawing electron, thus it means it will make the carbon is become more positive and it will be, the reaction will proceed smoothly. And move to the second factors, which is also support the first factors, is that how the Z is easily lost. So the better the good leaving group is, then the better the reaction will proceed. And then the last one is how good the nucleophile is. Yeah, the stronger the nucleophile, then the better it will attack the acyl chlorides. Okay, now talking a bit about the leaving group. A good leaving group, it will withdraw the electrons from the carbonyl groups, makes the carbon, leave the carbon become more positive. And this good leaving group, in this case such as the chlorides or such as the anhydrides, when they lose as the ions, they will form a stable negative ions. And acyl chlorides, it is it's better leaving group compared to the acid anhydrides. And then talking about the third factor that we saw before is about the power of the nucleophiles. And the best nucleophiles are the ones that are best at donating their lone pair. How readily it is to donate its lone pair. So the order of reactivity list is like this. So primary amine is a stronger nucleophile compared to the ammonia. Okay, and if you wonder why, yeah, it is because here there is the presence of R group. That the R group is act as the electron donating group. It will make the lone pair of the N is more readily to be donated as a nucleophiles. And then ammonia will be a stronger nucleophiles compared to alcohols, and least reactive nucleophiles is water. Alright, next is talking about the table on page 431. It is when we combine the acid derivatives with the nucleophile and what product that we would obtain. Okay, so let's take a look at the acid derivative first. We have two types, the acid chloride and anhydride. And as we mentioned before, the acid chloride is more reactive compared to the anhydride. Okay, and how about the nucleophile? Okay, so this it said that as we going up, right, the reactivity increase. But I think there is a typo here because before we already saw that amine is more reactive nucleophile compared to ammonia. Okay, so just switch this part if you wish. Okay, however, all the products will be just correct. Okay, so now let's start with, okay, just let's start with this one first. If we have ammonia with the acid chloride, okay, so this reaction, yeah, they undergoes addition-elimination reactions, or simply it is a nucleophilic substitution. So the ammonia will substitute the Cl. Okay, so we will get the NH2 group attached to this compound which next to the carbonyl. So we call it as the amide product. And when we work with an anhydride, we will get typical product, right? Because the same thing, that this good leaving group will be replaced by the ammonia, forming the amide. Okay, and then move to the amine, the most reactive nucleophile among them. So it will also again replace the Cl, giving you the NHR. And this is called the N-substituted amide. Yeah, because there is one alkyl group here, so there is one N-substituted amide. And the same thing when you react with anhydride. With alcohol, so this OH will, sorry, with the OR group will attack or will replace the Cl, yeah, forming an COOR group or ester. Here's the same. And with the water, the OH will replace the Cl, yeah, forming a COOH group or a carboxylic acid compound. Okay, now let's move to the mechanism of the reactions. Okay, first of all, we need to know what kind of reactions they undergoes. Again, they undergoes what we call as the addition, elimination reaction, or the nucleophilic substitution reaction. Okay, so the first one is a hydrolysis reaction. It means that we need the water as our reagent. So here we have ethanol chloride and water, they react together. So we know from the previous slide, right, that water here is actually a weak nucleophile. Okay, but however, because we work with like such a strong acyl chloride, so what happened that this lone pair of oxygen will attack the carbon atom, the partially carbon atom, and then expel the the bond between the CO towards the oxygen atom. Okay, and then we'll generate this intermediate product like this. So what you need to notice here is that, so now of course the O will have a negative charge because of the addition of the electrons here, and then this part, the whole of the water molecule will attach to the carbon, and thus because this oxygen, yeah, is supposed to be have two hands, but now it has three hands, so this oxygen bear a formal positive charge. Okay, and then yeah, what happened here is that, right here, this lone pair here, it will goes back. Okay, and then expel the good leaving group that we have here, the chloride, the chlorine here, and thus we could get our, yeah, transition product here. Yeah, this is the formation pack of the carbonyl, right? So you see, before the double bond becomes single bond, that's why we call it as addition reaction, and then the single bond become a double bond again. Yeah, so that's why we call this is elimination reaction. Okay, and this still attached, and then also the chloride ion that is being expelled off, and again these chloride ion are stable. And then the last step is that this chloride ion will grab the proton, right, and then goes, the single bond will go to the oxygen. Okay, so thus now we got our final product. Yeah, as we know, we will got the carboxylic acid compound. Yeah, in this case, it's ethanoic acid, and the H plus, if you want, H plus with the Cl minus will combine as the HCl. Okay, so here is the mechanism for the hydrolysis reaction. Alright, next, move to the other type of mechanism when ethanoyl chloride, yeah, the same starting material, but now react with slightly stronger nucleophile such as the ethanol. Okay, so you can see, yeah, all of the process already written here, but yeah, like before, it is like off the arrow, right? It's not yet a complete story. So I want you to pause the video and try to make the arrows that is needed. You need to be able to show how the electron is moved around, yeah, to produce the corresponding transition products and the final products. Okay, you can pause and try to do it. Okay, but yeah, let me just also give you some insight. Okay, so the first arrow we should draw is coming from this lone pair of oxygen for attack the carbon and then expel the oxygen, right? And thus you can get this transition product with the negative charge here and the oxygen bearing the positive charge. Okay, and then the same thing, this lone pair will goes back here, forming the double bond, expel the chloride ion, and you get this, oops, and I think I forget to put the positive charge here, right? And then the same thing in the Cl, this lone pair, oops, the lone pair of the Cl, it will grab the proton and goes to the oxygen, yeah, forming our ester compound. Okay, you can also add the name of the ester. Yeah, what is the name of the ester? It is the, this is the ethyl ethanoate. Okay, and then HCl as the side product. Okay, and then now here we change again the nucleophile with ammonia, also again slightly stronger compared to the alcohol before. And again, yeah, do the same thing, stop the video and try to draw the arrows that is needed to complete the mechanism. Okay, now let's check it out. So this lone pair of nitrogen will attack the partially positive carbon, expel the to the oxygen, and then forming our transition product. The oxygen bear the negative charge, and the nitrogen bearing a positive charge, right? Because nitrogen should be have 3 hands, but now it's 4 hands. So like 5 minus 4 is positive 1. So you have positive 1 in the nitrogen atom. Okay, and then this lone pair will goes back to the formation of the double bond and expel the chloride ion. Oh, yes, chloride ion. Right, so you got this transition product. Yeah, another transition product. Okay, and then yeah, here for the deprotonation process, right? Deprotonation process, you can call it like this. You can name it like this. So in this case, the proton will be taken by ammonia instead of by chloride ion. So ammonia will grab the proton, and thus for our final ultimate product is this one. Remember what is this product group name? It is amide. Amide. Okay, and then also we have the NH3 gain H plus become the NH4 plus, and the Cl minus is excess there, so forming the ammonium chloride salt. Okay, here's the overall equation. Okay, and then the very last mechanism, we have our strongest nucleophile here, a primary amine, in this case using the methylamine. Okay, so I think you already know how to draw the arrows, so let's just dive in. We have these, yeah, attack the partially positive charge and then expel it to the oxygen atom. Yeah, and also don't forget to put this sign, okay? And then yeah, forming the oxygen oxide ion and the N with the positive charge, and then the lone pair will goes down, it will be expelled off, formation of the second intermediate product, and then yeah, again this ammonia, okay, this ammonia or actually can be the our reagent itself, NH2CH3 can grab the proton. Okay, so either this or this, right? And then we will got again our product. It is a N substituted amide, or specifically the name will be N-methyl ethanamide. Okay, and also our side products, the ammonium chloride. Okay, so I hope yeah, that's all for the mechanism, and I hope that you understand the mechanism, because most of the question also will ask you how to draw the mechanism of that addition elimination reaction. Okay, now move to, yeah, we are at the end of the chapter here, the uses of acylation reactions. So acid anhydride is advantageous over acyl chloride as an acylating agent. Yeah, even though before we know that acyl chloride is more reactive than acid anhydride, but generally the company will prefer to use acid anhydrides. Yeah, the reason is because first it is cheaper, and then it is less corrosive, right? Knowing that, yeah, it's connect with the number 4, it's safer by the byproduct is ethanoic acid rather than HCl, right? Because if we use acyl chloride, our side product will be HCl, which means it is more corrosive. So the uses of acid anhydride is to prevent that corrosion process happen. And the third one does not react with water as readily, since acid anhydride is somewhat less reactive than acyl chloride. Okay, and then for the summary questions, you can try to, okay, page 433. Okay, I think that's all for the chapter 26.5, guys. See ya.